Hello, everyone. My name is Elias Maritan, and I'm a research assistant at Harper Adams University in the United Kingdom. Today, I'm presenting my latest research work titled Economically Optimal Farmer Supervision of Crop Robots. In recent economic literature on crop robots, it was demonstrated that autonomous farming has the potential for reducing conventional production costs, and that minimum production costs could even be achieved at smaller farm sizes and in irregularly shaped fields. Thus, crop robots on the one hand reduce the economic pressure on smaller farms, and on the other improve the environmental performance of crop agriculture. However, Lower van der Boer and colleagues demonstrated that if a constant human supervision of crop robots is mandated by law, many of the economic advantages of autonomous farming are lost. Because human supervision of crop robots is a key regulatory issue for autonomous farming, it is now highly important to understand what economic implication different regulations may have. By using a linear programming optimization model developed through the Hands-Free Farm research project at Harper Adams University, Lowen van der Boer and colleagues were able to calculate minimum wheat production costs for crop robots and conventional equipment scenarios. In this graph, the blue line indicates minimum wheat production costs for conventional equipment at four farm sizes spanning from 66 to 500 hectares. The orange line represents minimum wheat production costs for autonomous farming, and these are lower than conventional at all farm sizes. The labels on the two lines indicate the engine capacity of the autonomous or conventional equipment used, while the superscript labels show the number of machine sets used at each farm size. These results show that autonomous farming can have lower production costs, but these advantages would be lost in case 50% or more human supervision was required by law. In this study, we took the cost curves generated in Lower van der Boer and colleagues and compared them with four new scenarios to identify economically optimal crop robot supervision levels. That is, the amount of time that a farmer would choose to supervise crop robots even in the absence of regulations. By assuming that the farmer would choose to supervise crop robots for an amount of time that equates the time it takes to deal with minor crop robot issues, four incident scenarios were constructed by adding up various incident times to the baseline autonomous scenario published by Lowen van der Boer and co-authors. The specific incident times across drilling, spraying, or harvesting operations are shown in this table. We created two scenarios where a human supervisor is allowed to leave the farm and to travel back to the farm when problems occur, and two more scenarios where the human supervisor remains in the field and is occupied with other farm-related tasks. Each pair of scenarios was then characterized by either one or 10 crop robot incidents over an 8-hour day. The former were labeled as trouble-free scenarios and the latter as troublesome scenarios. In scenarios 1 and 2, total incident time includes 1 minute to respond to an incident, 5 minutes to travel to the crop robot, 5 minutes to resolve the issue, and 5 more minutes to return to the on-site supervision location, for a total of 16 minutes per incident. In scenarios 3 and 4, response time is increased to 5 minutes and travel time is increased to 30 minutes, for a total incident time of 70 minutes per incident. We then calculated minimum wheat production costs for the incident scenarios and compared them with the autonomous and conventional baseline scenarios drawn in blue and orange. The gray lines represent those two scenarios where the human supervisor operates the crop robots from a remote location, while the black lines represent those two scenarios where the human supervisor remains on site. The red circles indicate those troublesome scenarios with 10 incidents per day, while those without red circles indicate trouble-free operations with just one incident per day. These results show that in the case where autonomous operations are remote and troublesome, as in scenario 4, wheat production costs are always higher than conventional. If the human operator remains on site and operations are still troublesome, as in scenario 2, autonomous production costs are lower than conventional only at the two smallest farm sizes. Finally, if we look at the two trouble-free scenarios 1 and 3, production costs are lower than conventional at any farm size, but they are the lowest in scenario 1 for the smallest 66-hectare farm, and in scenario 3 for the three largest farms. The key results are that in case of trouble-free autonomous operations, as in scenarios 1 and 3, production costs remain substantially lower than conventional. In these cases, a human supervisor would choose to supervise crop robots for 13% of the time if on-site, or 25% of the time when working remotely. In case of the on-site and troublesome scenario 2, the farm manager would choose to use autonomous equipment at the two smallest farm sizes, but to switch to conventional equipment on the two largest farms. In scenario 2, the economically optimal supervision level is 43%. Finally, when operations are troublesome and remotely controlled as in scenario 4, production costs become higher than conventional at all farm sizes, and the required human supervision level is of 156% of machine field time. Thus, the farm manager in this case would either choose to remain on site to supervise crop robots 100% of the time, or to use conventional equipment instead. In other words, the economically optimal supervision of crop robots depends on three factors. 1. Whether a human supervisor is located on farm or off farm. 2. The frequency of crop robot incidents. And 3. The number of crop robots used in a field operation, which depends on the farm size and the engine capacity of the crop robots. The first implication of these results is that a regulatory requirement of 100% human supervision of crop robots would be an economic burden in those cases when the crop robots are relatively trouble-free, as in scenarios 1 and 3, where only 13% and 25% of human supervision was required, respectively. The second implication is for health and safety regulators, who should strive to balance the additional cost of a higher on-site supervision level and the reduction in human safety. Finally, a third implication is that researchers, entrepreneurs, and crop robot manufacturers should prioritize the advancement of artificial intelligence capacity so that crop robots are able to resolve minor problems without human intervention. Thank you.